This video will introduce the Clasius-Clapeyron equation, which is an equation to calculate vapor pressure. When given the heat of vaporization at a specific temperature, we will talk about what vapor pressure is and what can affect it. We will also work through a few problems by introducing a graphing method to understand how to use the equation under different situations. The first concept to understand is vapor pressure. Vapor pressure is the partial pressure of a gas in equilibrium above a liquid in a closed container at a certain temperature and surface area of the liquid. Think of it like this. If you leave a closed bottle of water on the counter, some of the liquid molecules are turned into a gas and are released from the top of the liquid. You can view this as condensation on the sides of the bottle above the liquid. Eventually, the rate of liquid becoming gas and of gas becoming liquid will be equal, and then a dynamic equilibrium is reached. It is called a dynamic equilibrium because the individual liquid and gas molecules are still changing from liquid to gas and from gas to liquid. This is when the vapor pressure is read at a certain temperature. Vapor pressure depends on temperature. The higher the temperature, the larger number of molecules that can escape the liquid phase and become a vapor. Therefore, higher temperature equals a higher vapor pressure. Vapor pressure also depends on the surface area of the liquid. The larger the surface area, the more molecules are near the surface, able to be vaporized, and the higher the vapor pressure. Vapor pressure also depends on the strength of the intermolecular forces. The stronger the intermolecular forces of the liquid, the harder it is for the molecules to escape the surface of the liquid, and the lower the vapor pressure. Vapor pressure follows Dalton's law of partial pressures. This law states that the total vapor pressure of an ideal solution equals the sum of the vapor pressures of each component times its mole fraction in the liquid mixture. A volatile liquid is one whose molecules are able to be vaporized enough to produce a significant vapor pressure at a given temperature. The higher the vapor pressure of a liquid, the more volatile it is. As you can see from this graph, less volatile liquids need a higher temperature to exert a significant vapor pressure, such as benzaldehyde, whereas liquids that are very volatile vaporize at lower temperatures, such as water. When the temperature of the liquid is high enough, the liquid vaporizes easily because it has reached its boiling point. When the vapor pressure reaches 1 atmosphere, or 760 torr, and boiling occurs, this is called the normal boiling point of a liquid. The Clausius-Clapeyron Equation is named after Rudolf Clausius, a German scientist, and Benoit Clapeyron, a French scientist, who are both founders of the study of thermodynamics. Thermodynamics is the study of heat energy in chemistry. Heat energy comes into play with the Clausius-Clapeyron equation with the heat of vaporization term, which is the amount of heat energy it takes to vaporize 1 mole of a liquid. The equation relates vapor pressure at a certain temperature with the heat or enthalpy of vaporization. There is not a linear relationship between temperature and vapor pressure. Rather, there is an exponential relationship. The equation is that the vapor pressure of a liquid equals a constant times the exponent of the negative of the heat of vaporization divided by the gas constant and the absolute temperature. To use the equation in a graph, take the natural log of both sides of the equation. Then the equation is the natural log of the vapor pressure, which equals the negative of the heat of vaporization divided by the gas constant and the absolute temperature plus the natural log of the constant. Then graph the natural log of the vapor pressure of the liquid versus 1 over the absolute temperature in Kelvin, and the slope of this straight line will be equal to the negative heat of vaporization divided by the gas constant. To solve for the heat of vaporization in terms of joules per mole, use the gas constant in terms of joules per mole times Kelvin. This value of the gas constant is 8.314 joules per mole times Kelvin. Another way to use the Clausius-Clapeyron equation is to relate two vapor pressures of the same liquid at two different temperatures. Then the equation looks like the natural log of vapor pressure of the liquid at one temperature divided by the vapor pressure of the liquid at a second temperature equals the heat of vaporization divided by the gas constant times 1 over the second temperature minus 1 over the first temperature. Pay attention to what order the variables are in this equation. It is the first vapor pressure over the second vapor pressure, but it is 1 over the second temperature minus 1 over the first temperature. To use the equation, we will have to use some algebra to solve for what is unknown with what is known. Almonds and cherries contain benzaldehyde, which is partially responsible for the odor of these fruits. Use the data in the table to calculate the heat of vaporization, delta, heat of vaporization, of benzaldehyde. First, they are asking you to solve for the heat of vaporization of this liquid, benzaldehyde. What kind of information did they give you to solve for this value? They give you a table of vapor pressures in torr and the temperatures in Kelvin, which is the vapor pressure of the liquid at various temperatures. To find the heat of vaporization, we could plug two different vapor pressures and two different temperatures into the equation, relating two different vapor pressures and temperatures. But this will only take into account two different vapor pressures. An easier way to do this that will take into account all the vapor pressures is to find the slope of the natural log of the vapor pressures versus 1 over the temperature in Kelvin. This equation is the natural log of the vapor pressure equals the negative of the heat of vaporization divided by the gas constant and absolute temperature plus the natural log of the constant. So let's add to the table by adding columns for the natural log of vapor pressure and 1 over temperature. Pause the video now to calculate these values. An easy way to calculate these values is to type these initial temperature and vapor pressure values into Excel and let the Excel equations do the work for you. To find 1 over the temperature values, type into one cell next to the temperatures column the equal symbol, then 1, then the backslash symbol, and then a left parenthesis. And then highlight the first temperature value, and then type the right parenthesis. To copy this equation to the rest of the temperature values, drag the equation down to the other rows. To take the natural log of the vapor pressure column, type into one cell next to the vapor pressure column the equal symbol, then ln, and then a left parenthesis. Then highlight the first vapor pressure and then type the right parenthesis. You can do this for each vapor pressure, or you can drag this first equation to the rest of the column. The values to be used in the graphing will be these. You will want to graph this data using a scatter plot, and then find the equation of the linear line. The units of this graph will work out because when you take the natural log of a number, it becomes unitless. So the units on the graph are 1 divided by Kelvin, and the units of the slope are Kelvin. The equation of the linear line that we got was y equals negative 5,871x plus 19.651. So the slope of the line is negative 5,871 Kelvin, which equals the negative of the heat of vaporization divided by the gas constant. The heat of vaporization therefore equals the negative of the slope times the gas constant. Since we have two negatives, this makes a positive. The heat of vaporization therefore equals 5,871 Kelvin times 8.314 joules per mole times Kelvin, which equals 48,819.8 joules per mole. Then divide the answer by 1,000 to get it into kilojoules and round to three significant figures. And you have an answer of 48.8 kilojoules per mole. Portable stoves used for camping often use pentane, C5H12, as fuel. A. If the normal boiling point for pentane is 36 degrees Celsius and its heat of vaporization is 27.6 kilojoules per mole, what is the vapor pressure of pentane on a morning when the temperature is 5 degrees Celsius? B. If the pentane is compressed into a portable stove, what will its boiling temperature be if the internal vapor pressure of the stove is 795 torr? Let's consider part A first. In this question, they are asking you to solve for the vapor pressure of pentane at 5 degrees Celsius. What kind of information do they give you to solve for this problem? They give you the normal boiling point of pentane and its heat of vaporization. The normal boiling point is a unique number because its definition is when the vapor pressure reaches 1 atmosphere or 760 torr and boiling occurs. So we know another vapor pressure and temperature as well. Since we know two temperatures and one vapor pressure and the heat of vaporization, and we are asked to solve for the other vapor pressure, we will use the equation that relates two temperatures and two vapor pressures. This equation is the natural log of vapor pressure of the liquid at one temperature divided by the vapor pressure of the liquid at a second temperature equals the heat of vaporization divided by the gas constant times 1 over the second temperature minus 1 over the first temperature. To use the equation, we will have to use some algebra to solve for what is unknown and what is known. Now, how do we find out what we need to know? Do we need to convert any of the units? We can just leave the one vapor pressure in atmospheres and know that we will be calculating the other vapor pressure in atmospheres as well. The heat of vaporization should be in joules per mole, so the gas constant units of joules per mole times Kelvin will cancel out. And both temperatures should be in Kelvin. To convert the heat of vaporization from kilojoules per mole to joules per mole, take the 27.6 kilojoules per mole and multiply by 1,000 joules per kilojoule, which equals 27,600 joules per mole. The temperatures will be 36 degrees Celsius plus 273.15, which equals 309.15 degrees Kelvin, and 5 degrees Celsius plus 273.15 will equal 278.15 degrees Kelvin. Our first temperature will be 309.15 degrees Kelvin, and our second temperature will be 278.15 degrees Kelvin. Then our first vapor pressure will be 1 atmosphere, and our second vapor pressure will be our unknown vapor pressure, X. If we substitute our quantities into our equation, our left side of the equation will be the natural log of 1 atmosphere divided by our unknown X. Our right side of our equation will be 27,600 joules per mole divided by 8.314 0.314 joules per mole times Kelvin times 1 divided by 278.15 degrees Kelvin minus 1 divided by 309.15 degrees Kelvin. We can solve for the right side of the equation. First, it is best to handle the temperatures by dealing with each one separately. 1 divided by 278.15 equals 0.003595, and 1 divided by 309.15 equals 0.003235. Then, to subtract these two numbers, 0.000361 over Kelvin. Then multiply this times the heat of vaporization divided by the gas constant, equals 1.195. The units of this number work out to be unitless because the units of joules cancel out, the units of moles cancel out, and the units of Kelvin cancel out from the temperature terms. Now, to solve for the unknown vapor pressure, which is captured by the natural log term on the left side of the equation, all we need to do is to take the opposite of the natural log of both sides, which is the exponential term. Taking the exponential of the left side gets rid of the natural log term, so we are left with 1 atmosphere divided by our unknown vapor pressure. Taking the exponential of the right side is e raised to the 1.195, which equals 3.304. To solve for the unknown vapor pressure, take the 1 atmosphere and divide by 3.304, which equals 0.303 atmospheres rounded to 3 significant figures. Does this answer make sense? Yes, it does, because as we lower the temperature, we also lower the vapor pressure. For part B, they want you to find a new boiling temperature, given that the internal vapor pressure of the stove is 795 torr. We also know our heat of vaporization from part A, and we also know 2 other vapor pressures and temperatures. Since we know 2 temperatures, and more than 2 vapor pressures, and the heat of vaporization, and we are asked to solve for another temperature, we will use the equation that relates 2 temperatures and 2 vapor pressures. This equation is the natural log of vapor pressure of the liquid at 1 temperature divided by the vapor pressure of the liquid at a second temperature equals the heat of vaporization divided by the gas constant times 1 over the second temperature minus 1 over the first temperature. To use the equation, we will again have to use some algebra to solve for what is unknown and what is known. Now, how do we find out what we need to know? Do we need to convert any of the units? Since we are given a vapor pressure in torr, we should express our other vapor pressure in torr. The easiest way to do this is to remember that 1 atmosphere equals 760 torr. So our normal boiling point of 309.15 degrees Kelvin happens at a pressure of 760 torr, which we will leave as our first temperature and vapor pressure. Then our heat of vaporization is equal to 27,600 joules per mole, and our gas constant is still 8.314 joules per mole times Kelvin. If we substitute our quantities into our equation, our left side of the equation will look like the natural log of 760 torr divided by 795 torr. Our right side of our equation will be 27,600 joules per mole divided by 8.314 joules per mole times Kelvin times 1 divided by our unknown temperature, here X, minus 1 divided by 309.15 degrees Kelvin. We can solve for the left side of the equation. The natural log of 760 divided by 795 is equal to negative 0.04502. Then transfer the things which are multiplied by the temperature terms to the left side of the equation. Our ultimate goal is to get the x term on a side by itself. We will multiply each side of the equation by the gas constant of 8.314 joules per mole times Kelvin, and divide the heat of vaporization of 27,600 joules per mole, which equals negative 0.00001356. The units of this number are going to be inverse Kelvin, because the torr cancel out each other before we took the natural log of the number, so our joules and our moles canceled out, but our Kelvin did not. Negative 0.00001356 inverse Kelvin equals 1 divided by x minus 1 divided by 309.15 degrees Kelvin. Now to solve for our unknown temperature, take the 1 divided by x to its own side of the equation by adding 1 divided by 309.15 degrees Kelvin to both sides of the equation. 1 divided by 309.15 degrees Kelvin equals 0.003235 plus a negative 0.00001356 equals 0.003221, 1 over Kelvin. Then to solve for x, just take the inverse of this number, which equals 310.5 Kelvin. Does this answer make sense? Yes, it does, because as we raise the vapor pressure, we also raise the temperature.